Ok, já apareceu o aviso.
Sim, pode começar, já está no YouTube.
Então, boa tarde a todos. Estamos aqui reunidos virtualmente para a defesa de qualificação de doutorado do candidato Muhammad Asmat. O Muhammad Asmat ele é funcionário da Agência Espacial do Paquistão, está aqui com uma bolsa da Comissariado de Altos Estudos do Paquistão, e nos juntou ao grupo aqui há uns 3 anos e um pouquinho, né? E se espera que a tese dele seja concluída no final do ano. Participam da banca como membros externos o professor Lúcio Dornelles, da Universidade Federal de Santa Maria, especialista em junções túnel, o doutor César Buffon, do Laboratório Nacional de Nanotecnologia, professor, doutor, estou usando agora a nomenclatura da FINEP, né? Do doutor João Paulo Sinecker, que é do Centro Brasileiro de Pesquisas Físicas, o Diego Ernesto Gonzalez Chaves, que é co-orientador, e eu, o Ben Sommer, que sou orientador. Bom, então, com a palavra, o Asmat tem o período regulamentar aí para fazer sua apresentação, depois a gente passa para a etapa de arguição pela banca. Tá bom?
Posso começar, por favor?
Você tem que compartilhar sua tela, né?
Sim, ele está autorizado ao compartilhamento. Quando eu entrei, estava testando, né?
Sim, ele pode compartilhar. Está
Pode
autorizado.
compartilhar. Ele já fez um teste, inclusive. Ah, ok.
Can I start, please?
Yeah, you can start.
The present PhD project is about the study of dynamic properties and response optimization of magnetoresistive nanostructures. My name is Muhammad Asmat. My supervisor name is Ruben Luis Sommer, and my co-supervisor name is Diego Chavez. In the last few decades, spintronics has got great interest because of has a great interest in a nanotechnology because of these features, and it has along with this, spintronic devices are non-volatile, fast. Here on a time scale you can see here, power saving, cheap, and less heat dissipative. These have applications in a nanotechnology, read-write head, memory devices, etc. Thesis proposal is like this. I will study the study of static, dynamic, and transport properties of magnetoresistive multi-layer structures. Route towards the goal is like this: fabrication of exchange bias and synthetic antiferromagnets, and study system characterization of damping and line width in microwave ferromagnetic mode. Then the production of spin valves, and study their static, transport, and dynamic properties. The structure of a project is like this. I have fabricated exchange bias and synthetic antiferromagnets, and use them in a different kinds of a spin valve and magnetic turning junction of different kinds of spin valves like cobalt iron based, nickel iron based, and seed layer based spin valve. Overall, our structure of project is I will study overall static, dynamic, and transport properties of the system. Summary of my talk will be like this. In the introduction, I will introduce magnetoresistance, spin valves, and in a review fundamental background, I will review about GMR, TMR, and synthetic antiferromagnets dynamic properties. and transport properties. In a results section, I will conclude the results, and finally I will conclude, and the next step I will do in my project. In a spinware comprised of two ferromagnetic layers, one is called free and the other is called reference layer. Reference layer is pinned with a anti-ferromagnet to fix its coercivity so that in operation it will not change its direction. Here you can see a free layer. Here you can see a parallel state when orientation of a magnetization is parallel with the orientation of a magnetization in a reference layer. You can see a reference layer orientation of a magnetization is upward, and orientation of magnetization in a free layer is also upward. You see a low resistance and lot of polarized currents passes through the spin wire. Similarly, for a high resistance state, when the orientation of magnetization in a free layer and reference layer are anti-parallel, you can see here this spin valve has a high resistance and low polarized current will pass through the spin wire. Here you can see a static characterization of a spin wire. You can see a anti-parallel state here when the spins are in a anti-parallel direction, and this is a parallel and this is a parallel but opposite direction. This is a transport characterization. You can see a high resistance state when the spins are anti-parallel state, while the low resistance state here you can see when spins are in parallel direction. Here, giant magnetoresistance can be explained with the help of two-channel model by represented by a mode. In the he assumed the during the process he assumed the spin scatterings are neglected, and he reserved two independent spin channels for the conduction of spins. Here you can see as I already explained, parallel state and anti-parallel state. Here you can see for a parallel state, this arrow shows a spin in a resistor model. I will explain this in a two resistor model. For this is arrow represents a spin up electrons, and this arrow represents a spin down electron. You can see for a spin up electron, there is a low resistance state. Here, high current flow through the spin valve. For a anti-parallel state, here the reference layer is this one, and the free layer. There is an anti-parallel configuration. You can see for up electron, there is as they are like upward direction, there is a low resistance. Here is a high resistance. Similarly, procedure can be adapted to explain for a spin down electron. Similarly, when incident plane wave is incident on a barrier, if the barrier thickness is very thin, then this wave become evanescent and transmitted through the other side of a barrier. If the barrier is thick, very thin, then the conductance between conductor here in the PMR conductance also occur by two independent spin channels, and conductance for a parallel is proportional to the product of a spin up and a spin down. Similarly, for anti-parallel, conductance is proportional to and PMR is equal to the difference of resistance in a anti-parallel to parallel state. Synthetic antiferromagnets are a tri-layer system in which two ferromagnets are separated by a non-magnetic ruthenium metal, and the interaction between the two ferromagnets can be mediated with the help of ruthenium, and this interaction can be this kind of interaction is a long range. Depending upon the thickness of a ruthenium metal, this interaction can be a ferromagnetic, and anti-ferromagnetic. Here on a right hand side, you can see the equation for here J is a exchange coefficient. This is a M1 and M2 is a magnetization of a ferromagnet 1 and a ferromagnet 2. Here you can see for positive J value, we have a ferromagnetic interaction between the ferromagnets. For a J negative value, we have anti-ferromagnetic interaction between. The nature of a coefficient of J is kind of oscillatory. Evolution of a magnetization can be explained with the help of a Landau, Lifshitz, Gilbert, and Slinkowski equation. The first term is when the moments are placed in the magnetic field, then they precess around the magnetic. They precess around the magnetic field. Like the first, the Landau-Lifshitz equation. First term of a Landau-Lifshitz equation is explaining the precessional motion without any loss. But experimentally, we see that there is a loss in a, when the moments are placed in a magnetic, we see the loss in a, this second term is added because of a damping of this precession of moments. And then the third term includes the Slinkowski term is called Slinkowski term, which is a spin transfer torque term. Here, the effective field can be measured with the help of first derivative free energy, and we know that the free energies, magnetic free energies in a magnetic system can be of exchange energy, Zeeman energy, and isotropic energy, magnetostatic energy. The exchange energy arises due to the interaction between the spins of the magnetic system, while the anisotropic energy is related to spin orbit coupling, while magnetostatic due to the poles of the magnet. Zeeman energy arises due to external magnetic applied field, and the exchange device is due to the interaction of ferromagnet with the anti-ferromagnet. Now the spin about spin transfer torque, spin polarized current can carry enough angular momentum for transversal of this free layer. The spin transfer torque arises due to the misalignment of a free layer with respect to a hard reference layer. This you can see here. This is a magnetization of a free layer. This is a magnetization of a free layer with a cross product of a magnetization of a fixed layer. We can observe from this one, the spin transfer torque is only observed when the magnetizations are when we have a non-collinear system. That is when the angle between the free and fixed magnetization is not equal to spin transfer torque is observed when the angle between the free magnetization and fixed magnetization is not equal to 0 or 180 degree. Ferromagnetic resonance. If the frequency of a AC field we apply to a system which is precessing around the effective magnetic field, if the frequency of a AC field is equal to the precession frequency of a applied field, precession frequency of a magnetic moments, we observe the we observe the resonance, and energy is absorbed by the magnetic system. Experimental techniques. In experimental techniques, I will explain the growth of samples, and then I will describe the characterization techniques for static measurements, for transport measurements, and for dynamic magnetization measurements. Sample was prepared with the help of AJA magnetron sputtering. Here, there is a physical process showing here where when the argon ions are ionized and accelerated towards the target and injected the atoms of a target, then these target atoms are accelerated towards the positive node. This is a physical process of sputtering. While this is a pictorial description of our sputtering system. Here is a main vacuum chamber with a high vacuum. Here we have it has a capacity of 6 targets. These targets are connected by either by a DC field, DC RF field sources, and DC field sources. This is a load log. We can replace the sample from a main chamber without breaking the vacuum of a system. Here we can apply a uniaxial anisotropic field of a 200. It has a capacity of application of a uniaxial anisotropic field of 200 oysters. This is a description of a torrents. we can place our samples here. Depending upon the quality of a thin film, we can vary the working pressure. Working pressure during deposition, we can vary this one, and we can also vary the argon pressure in a vacuum chamber. For a complex fabrication of a complex samples, we also like current perpendicular to the plane. You have to use successively magnetron sputtering, lithography, etching, equipment. There is a 13 steps. This process take almost 13 steps due to for fabrication of a one sample. This takes a 13 step. It is a 13 step process. But due to some reason, we could not use the plasma etcher. Therefore, for CPP samples, I have used the physical mask, physical copper mask, which I have prepared using lithographic techniques. Static magnetization characterization were done with the help of AGFM and VSM. The AGFM has a field range of 600 oersted, while the sensitivity is -7, which is enough for the for measuring the static characterization in this project. If we need a high field, we can use a vibrating sample magnetometer with a field range of 90 kilo oersters. Four probe technique is used for measuring the transport properties of my sample. I have used this technique. Here you can see a sample is placed. There are four probes, and the Helmholtz coils for used for field sweeping. And I have used a semiconductor device analyzer for measuring the transport properties of my samples, and I configured the semiconductor device analyzer as like this. Semiconductor device analyzer has a 4 SMUs, that is 4 source meter units. I have configured these 4 SMUs as this one, like this. The SMU1 I have used like a variable current source. SMU4 is variable current source, and then these two SMU2 and SMU3 are used as a constant current source. I make sure that the current flow through SMU2 and SMU3 is zero, so that it behaves like a constant voltmeter, so that I can measure the voltage difference of a device under test by using this. Here I can measure the current, here I can measure the voltage, and by measuring current and voltage, we can get easily a magnetoresistance of this device under test. Ferromagnetic resonance. With the help of VNA FNR, we can explore the magnetization dynamics of our magnetic system. This VNA FMR consists here. It consists of a wave. We have a waveguide here. Sample is placed on a waveguide. Here, for a AC field, we apply a AC field through this central conductor, through the VNA, and the DC or sweeping field which is required, we apply through CAPCO. This is a source of a DC field. We apply a DC field to the waveguide. The output from a VNA FMR is like this. We call this one is a color map, and this we can study the magnetization dynamics of a magnetic material in a saturated and unsaturated state, and the power absorbed can be measured with the help of a transmission and reflection coefficients. Or VNA has a two-port system, can measure the S parameter figure. Due to waveguide kind of nature we use, we can explore up to many broadband frequencies. We can apply from 10 megahertz to 24 gigahertz. It has a sensitivity, wide range, and output up to 63 milliwatt. Here, after getting the color map, this is the absorption power by the system color map. You can see we can extract information from this color map by using two techniques. Here, there is a color scale. Here, zero represents blue represents zero, and this is the maximum power absorbed colors up to one. We can measure we can extract information this color map by using two methods. One by fixing frequency, like this here, fixing frequency, and varying field, like we have varied field from 300 to minus 300 to 300 by fixing the frequency 1.5 and then 3 and 4.5. We got these amplitudes, that is maximum power. The resonance occurs here, the maximum power absorption, and then similarly we can fix the field and sweep the frequency. Sweep the frequency. Here we get a scan of fixing the field of 20, then 150 and 300 branches with maximum amplitude corresponds with the oscillation modes in a magnetic material. We can analyze anisotropic in the system with the help of a color map, line width and damping constant. With the damping line width and damping constant can also be measured with the power derivatives. We can measure the relative amplitude of the peak. You can see here the relative amplitude of the peak by fixing frequency and fixing field. In the project results section, I will present it result. First of all, started from exchange bias. Then I will present the result of synthetic antiferromagnet. Then I will present the result of a spin valve, and then finally I will represent the result of a magnetic turning junctions. Here in step one, I have prepared the different exchange bias system by using magnetron sputtering. The exchange bias system were prepared, different exchange bias samples were prepared by using cobalt iron, nickel iron, and seed layer based system. By choosing different thickness of a cobalt iron, we have prepared different exchange bias to be used for in a spin valve and a magnetic turning junctions. Here you can see first on a left hand side there is a soft ferromagnet nickel iron. Therefore it has a less coercivity, and this exchange bias has a potential application in sensors. And this is a exchange bias of a hard ferromagnet, that is cobalt iron pinnet with a medium manganese. These exchange bias, furthermore, these exchange bias are produced without any heat treatment. The other exchange bias is a seed layer based. Here I use the nickel iron of a seed layer of a nickel iron of 5 nanometers, and then on the top we end up with, at the top of structure we have a nickel iron, so that this means that we can, and because ferromagnet ends at the top, we can use this thing as a for measuring the inverse spin Hall current. That here you can see that this is a main exchange bias, and this effect is due to the seed layer. Here you can see 5 nanometer of a seed layer. Seed layer is used to get the adequate crystal structure on the medium manganese. Step 2, I have prepared different synthetic anti-ferromagnets as well for to be used in for their dynamic magnetization studies, and to be used in spin valves and magnetic turning junctions. Here, this is a nickel iron base. I have choose the ruthenium thickness as a -8 and 0.95, so that the interaction between two ferromagnets is there is a lot of interaction, high interaction between the ferromagnets. Here these are ended with a platinum, ruthenium, and a tantalum at the top. Here I have also produced a synthetic antiferromagnet with a nickel iron At the top, you can see here, this system can be with the heavy metals at the top. This can be used. This system can be used to measure the inverse spin Hall effect like this. That is the spin pumping with the help of VNA FMR. We pump the spins in the heavy metal and then measure this charge current from this heavy metal. So different synthetic antiferromagnets were prepared. That is, you can see here. This with the ruthenium thickness of 0.8, and then this one is with a seed layer with a ruthenium thickness of 0.95. Here you can see respective static magnetization behavior of a SAF. Here you can see a saturation region where the Zeeman energy is dominated over a spin flap and antiferromagnetic coupling energy. You can see this is a antiferromagnetically coupling region, spin flap region, similarly spin flap region and saturation region. Similar explanation can be made for this system here, but there is due to this loop is due to this seed layer around, but this does not have any effect on the properties of a synthetic antiferromagnet. We have already done work on the non-interlayer coupling in spin well study by VNA FMR. You can see we have our own model, numeric model to explain the interlayer coupling, and by using this model we can also extract anisotropies in our system. Here this is a synthetic antiferromagnet with a seed layer based system. You can see respective dynamic modes, oscillation mode with respect to antiferromagnetically coupling region and this region. Here in this, I have chosen this region. Then I have measured the FMR absorption derivative of this region. Here I did the measurement like this. I have fixed the field. Here you can see a blue line here. I have fixed the field. Then I sweep my frequencies from I sweep the frequencies from 2.5 gigahertz to 5.5 gigahertz. That is measurements were done at different fixed field, like red represent at I have fixed field at 30. This green is a 0. This purple is a minus 30, and this blue is a minus 60. Then from this peak to peak ratio, peak to peak value, we can extract the damping constant, and this represents the resonance frequency. We can measure the resonance frequency from here. The measurements dB by dH is done with at a perpendicular direction, that is in a z direction, because in a parallel it is very difficult to find the derivative of this in this unsaturated states. This unsaturated state. Step 3 is the production of a different spin wells based on a cobalt iron and nickel iron, cobalt iron seed layer base. And you can see for the optimization of a MR value, I have changed the ferromagnetic thickness of a ferromagnetic layer and a non-magnetic copper. I have the cobalt iron thickness was chosen as 3, 5, and 10 nanometer in each case, and value. Similarly, the cobalt iron based and a nickel iron layer are and a cobalt iron as a seed layer. The good thing about this sample, we have got the MR value without annealing spin well. We got a GMR without annealing the bottom spin well. The spin well, first of all, I have shown this is a cobalt iron of a 10 nanometer. This is a reference layer, and this is a non-magnetic. I have varied. This is for a Upper 1 nanometer, I have got a MR value of 4.8. Then I increase the thickness 1.5. The magnetoresistance is increased, and for the thickness is further increased. I have got more than 7%, and for a thickness of 2.5, I have got a MR of 9.3%. Further to this, I have reduced here. I have reduced the thickness of ferromagnetic cobalt iron, free and pinnet layer. And by fixing the copper 2.5, I have got a magneto-resistance around 6.1%. Similarly, for a cobalt iron, I will further reduce the thickness of ferromagnet to 3, and 3, this combination give me a magneto resistance greater than 4%. I have used here I have used a nickel iron as a free layer. You can see nickel iron 3 nanometer. I have got a magneto resistance of a 3%, and for a nickel iron free layer as a free layer, I have got a magneto resistance of 5%. This can be explained by the spin polarization of iron, cobalt, and nickel. That is the one of the parameter for getting the high MR and dependence of MR on a spin polarization of metals. That is, we know that iron has a better spin polarization than cobalt and then nickel iron. This is the one of the reason for getting the low MR value in the case of a nickel iron, and in the case of a nickel iron. Here in a bottom pin, I have used in a bottom pin spin valve, there is a use of a nickel iron as a seed layer, and then in this system I have used a cobalt iron as a seed layer. Here you can see only a seed layer is different. Other the pillar of a spin valve is same. You can see a magneto resistance in this case is a 4%, while this sample is annealed one. Without annealing, it also has a magneto resistance of 4%. I annealed this spin valve system at 170 for 30 minutes. Then I have got the increased value of a 3% in this case. The unannealed samples both have the same magneto resistance. This implies that the seed layer does not have any effect on the magneto resistance of the spin valve. Result summary is that cobalt iron based spin valve, nickel iron base, and seed layer base. We have got on a seed layer base up to 7% with annealing, and without annealing, I have got a maximum value of a 9.3, MR value of 9.3 with cobalt iron based spin valve. Here, step 4, I have also prepared the magnetic turning junction, the stack of this with metallic aluminum. Then I have oxidized aluminum. Under these conditions in our sputtering chamber, oxygen flow was chosen as 30 SCCM, argon flow 15. I have working pressure for growth of films. I have chosen 25 millitor and plasma exposure like 60 seconds. Here you can see anti-ferromagnetically states. Then these are the saturation states. For MgO, here you can see I did with the cobalt iron. This is a static characterization. While for when I choose the cobalt iron boron, this has a composition of 20, 60, 20. I have measured the different exchange bias with the cobalt ferro boron 20, 60, 20 with iridium manganese, different thicknesses of iridium manganese. I could not get the exchange bias of this cobalt iron boron, which has a composition of 20, 60, 20. There you can see here a static characterization of this cobalt iron boron. Therefore, I choose another method. I stack I use a synthetic antiferromagnet to build a exchange bias in my magnetic turning junctions. Here you can see I try to make here you can see a flipping This is a free layer, cobalt ferroboro. Then I have used this synthetic antiferro. I try to make a synthetic antiferromagnet so that it has, because we know that this has a exchange bias with the remedium mechanism. You can see a exchange bias effect here. This is a switching of a free layer here. Then I did the structure analysis of my magnetic tunneling junction samples. This is an annealed. I have annealed my sample at 280 degree for 1 hour. Then I have annealed my sample at 310. Then annealed at 340 C for 1 hour. You can see MgO was grown as a 22002 structure, while which is considered basic for getting the high GMR, high TMR values. In conclusion, our sample shows good exchange bias with nominal coercivity without any thermal treatment, with ferromagnetic layer on the top, which is an important feature for the application of this system in spin Hall, inverse spin Hall effect. Our spin valve shows the GMR ratio up to 9.3%. And while the bottom pin spin valve shows the GMR about 7% with annealing. The magnetization curve of SAF shows well-defined three regions of free and pinned layer, namely parallel, anti-parallel, and spin flop region. The dynamic properties of SAF shows good features of a pinned and free layer. Surface study of MTJs was carried out at different temperature, which reveals that we are able to produce MTJs with MgO002, which is a basic factor for getting higher TMR. Here, the further step will be to measure the line width and damping constant of our magnetic systems. Here you can see by fittings. By fittings, we can get the coupling constant, different magnetic parameters we can get by fittings. Here you can see in a static curve, you can see a free layer is switching independently from the reference layer. The result you can see here, the coupling from our fittings, we have got the coupling coefficients like 0, which is 0, and 3 oersted, which is expected due to this free layer is switching independently. Similar, this is experimental data. This is our simulated data with our software. Similarly, these modes are simulated. Here you can see this is. Thank you.
Ok. Obrigado, Asmat. Vamos passar para a parte de arguição, então. Acho que, por questão de distância, eu vou passar a palavra para o professor Lúcio Dornelles, de Santa Maria.
Ok, Rubem, eu vou...
O Asmat, descompartilha aí, só se precisar você compartilha de novo a tela.
Stop share?
Oh, unshare. Stop sharing.
Okay.
So I'll speak in English or?
Yeah, English is better.
Maybe it's better in English for him.
Okay, that's great. No problem. Okay, first, I'd like to thank you, Asmat, and Rubem, and Diego for the invitation. It was an opportunity to get to know about your work and what Rubem is doing now. So what I did is, I'm not sure whether this text is going to be used in your thesis, but anyway, I did some comments on the PDF directly, and then I'll send it to you so you can check my comments and suggestions straight there. But I'd also like to make a few comments here and ask you a few things. So let me check. First, I liked your presentation, and I found it nice. Your text is also, of course, it needs some checking with some small things, but this is quite
Just a
normal.
second, Lúcio, teu som tá muito abafado, não sei se ou tá muito alto ou tá muito longe.
Tô aqui no tal, tô no... Então, de repente eu desligo aqui esse fone de ouvido, vou tentar.
Você que sabe. Vocês estão ouvindo bem, pessoal? Os demais membros da banca? O Lúcio?
Sim, dá para entender. Tá um pouco grave demais, mas dá para entender.
Talvez um pouco grave só. Bom, continua, Lúcio. Continua.
Okay. So I'll send it to you. So this is small comments, but anyway, I liked your presentation. It's really nice, and your presentation of the text is also clear. And so let's go to my questions.
Okay.
So at the text, and also I believe it's your slide number 7. You just say that you have an increase in the resistance when the magnetizations are parallel in both electrodes. It means that the low resistance is also parallel, is always parallel when the magnetizations are parallel, and high resistance is when they are anti-parallel.
Yes.
Is that always like this?
Yes, Professor. In spin wave system, this is like this in a magnetoresistance. When the orientation of a magnetization is parallel, we guard like this. When the parallel they are.
And in tunneling junctions, would it be the same?
In
the tunneling junctions, tunnel junctions.
It is because you know there is there are several other parameters on which TMR depends. Like when the TMR may be increase or decrease depending upon the angles between the fixed layer and free layer, and then there is another effect of a temperature and barrier characterization is also important for this one.
Yeah, that's the thing.
These are other parameters.
It may not be always positive. Maybe negative.
Yeah.
And then okay. Go to the next. So another interesting thing, like you produced a lot of samples, and you probably have a lot of results, and so on. So that's very interesting. And one thing that is in your text on page, let's see, 17, you show a table with the deposition rates and so on. That's very interesting because when we work with some new material, we may not know what's going to be the sputtering rate or the growth rate. So that would be nice to compare your table with the tables we find on the internet, or if you look for sputtering yield and so on. So that would be very useful information for whoever is growing materials. And then I think you should just check, maybe it will be easy to do, and then you can comment on whether you're finding the expected growth rates that you see in some other, because that's Now, okay. One general comment on the magnetization measurements. In your text, I'm looking at the figure 4.1. So you have two, you showed it in the presentation also.
Yeah, I will share the presentation here.
Don't worry, because it's just because you could just, that particular figure, whenever you can do this, you should keep the same scale, yeah, because then you can compare and see exactly where they are going to be the transition, what are the fields where the transition magnetization changes. And another thing is that if it's possible, I mean, I would suggest you to change magnetic field H to μ0 H, and then write them millitesla, because then you'll be using SI units, and it's just a factor of 10, like, so if you go from millitesla to Worsted or vice versa, you just need to multiply or divide by 10, and then you'll be using SI units.
Okay.
But that's not, it's just I refer to. I believe that for the ferromagnetic resonance and so on, it's not so easy to use the SI units. Now, you show one figure, figure 4.4.
4.4.
Yeah, it's very interesting. I'm not sure if you have it there. If you can show
Asmat, you may share this presentation, show people the figure
if you
we're
have this
talking about.
figure.
It's better to the audience.
Okay.
Share the PDF for your file.
Page 27. It's in the text is 4.4.
Okay, I will open the text.
It's
Yes, I will.
some spectrum.
This one, can you see please?
Yes.
Okay, 4.4.
Yeah, it's page 27, I think.
This one?
4.4?
Figure 4.4? Okay. This one. I cannot hear you, Professor.
So,
the voice.
Okay, now what happens at around 4 gigahertz? Because if you fix the frequency at 4, I think you get like 4 peaks maybe.
Professor, here I have fixed the field and then vary the frequency from 2.5 to 5 gigahertz. And this is a power derivative with respect to
What
perpendicular.
if you do the opposite? If you fix the frequency and
Yeah,
then
Professor, our group has already did this thing, na? Fixing the field and fixing the
okay,
frequency and measuring the field.
okay,
This,
but but is there anything interesting at around 4 gigahertz? Because then it seems to be different because you would
yeah.
get like 1, 2, 3, 4 peaks, right?
No, Professor, this is a four measurements, na? One at a fixed field of
Okay, I
zero.
know, but just go to the next figure. I think then you can see what I mean.
Oscillation,
4.5.
you are power absorbed. This one?
Let's see. Yeah,
Yeah.
if you get, yeah, that's interesting.
Yeah. Professor, I did not put a, I could not put a power absorbed equation here. If it the that equation is here, it is better to understand this thing. Na? That power absorbed equation has three components like amplitude, temporal components of a magnetization, how magnetization varies with time, and then another is a AC field. This is a vectoral component of a vectoral components of a magnetization changes.
You have some one figure where you have the frequency fixed and then you change the field
No, Professor, I don't
from.
have because I am
Okay,
measuring like fixing field and varying the frequency.
okay. Now I have one last question. Would be your figure? It's on page 31, I think, or it's 4.11.
4.11.
Yeah, it's the X-ray diffraction of the,
Yes, Professor.
that one. Yeah, you see. Now, I have a few questions from this figure. The first would be, what are the peaks at around 30 degrees?
Uh, from literature review, here you can see a peak of a tantalum 002 around from the between the 30 and 40. I have marked this one.
Below that one, and the other small ones below that. Do you know what they are?
I did not see in a detail of these weeks. This
Okay.
and above 18, because I want to see
Okay.
the only the peaks of the MGO, how I
Okay.
grow this MGO.
Okay. Okay. But would be interesting to have at least check because the X-ray diffraction is very sensitive, and then you may find something interesting. I don't know. I'm just guessing.
Okay.
The important thing there is that that peak just above 60 degrees.
Yes.
You see, you say that that's MGO 220, but I can assure you it's not. Okay, and there's a simple reason for that. You see, you have the peak for the MGO 002 there.
Yeah.
See,
Yeah.
okay, so if this peak at 60 were MGO, it would be wider. Okay, there's no way of a peak from the same material be thinner at higher angle because the width of the peak, you can see that famous Scherer equation. I'm not sure if you're, but you see from the Scherer equation that the width of the peak for the same material, let's say the crystallites that are giving the 002 peak are the same crystallites that are giving the 220. So they have the same size. So if you if you isolate the width in the Scherer equation, you see that as you go to higher angles,
Yeah.
the width has to increase.
Yeah. Yes.
Okay, so the same thing may be valid for the one that you say is cobalt iron 002. They are very, the width is very small, so I don't think they are from your sample. You see that most peaks, they should be wide because the films are thin. But anyway, this is not MGO, I can assure you, because the width should be, I did some calculation, but it should be at least 10% wider. Okay. But I think it may be the reflection from the silicon, that's the one at 69 point something. So this could be the K beta radiation. So this may be the peak from silicon with the K beta component of the radiation, because you cannot kill it 100%. You have to check, but I would guess this. And maybe it's the same for other the small peaks. But anyway, I'm sure that this is not the peak at 60 is not the 220. Because it could not be so thin or so sharp as it is. The width should increase at higher angles, not decrease. Okay, that's one. That would be. Anyway, you see the MGO 002, so that's fine. I mean, I'm convinced that you have the MGO that you want.
Because I have also read a thesis from University of Santa Maria. No? I have rechecked these peaks with that one. I have checked that.
Maybe one of that's another thing I wanted to tell you. Like one of my students, he also worked with tunneling junctions, and then we didn't use the same. We made simpler junctions, but the barrier, the tunneling barrier, was actually equivalent as yours may be. So if you have any problem during the measurements, I mean, it would be nice to talk to him, because it's tricky to make the measurement, because they're very, very sensitive.
Yes.
And maybe just if you try to measure some by now, you get this feeling. Right? It may not be easy to measure, because they may break, like electrically break quite easily. But anyway, if you need help. So okay, but that would be my comment. And so another comment, I'm not sure how it works in real, but of course you don't need to change the text, but one important thing would be you have at least some dates fixed, like, well, I intend to do this I know it would be harder now to do this, to set dates for doing things, because we are not, we may not be able to get to the lab and do things, but anyway, at least you may be able to say, look, if everything is back to normal, I could do this in 1 month or 2 months and have some idea of how much time you need. That would be nice. I understand that you may have this in another version of your plan, but you have an idea of what are the plans.
Yes, Professor. I have already made the anisotropics of my synthetic anti-ferromagnets. I have not included in this presentation. Almost it will take around 1 month to measure the line width or damping constant and the other parameters like magnetic anisotropies as well, if I redo these ones.
Okay. Okay. Well, congratulations on your work. I like
Thank
it
you.
very much. I believe you have a lot of samples and results, and it's going to give you quite a hard work to interpret everything. But I'm convinced that you have everything that you need to complete this plan, because I believe that having the samples or being able to produce and analyze the basic characteristics of the samples, it's
you automatize things, you assume that you know, but you simply do things. Yeah. For instance, when you do sputtering deposition, yeah, you do an argon background. Yeah.
Yeah,
Do you
yeah,
know
yeah.
why?
Because argon is almost everywhere used as a ionized gas in a sputtering. Na?
Yeah. Then
Yeah,
when you control the
yeah,
pressure, what you do exactly during
yeah,
with your
we
process?
have a highly sensitive pressure valves in a sputtering chamber, na? Through which we can control the flow of argon. We can introduce other gases like oxygen for oxidation of like I did for oxidation of aluminium to aluminium oxide. I did the
Mhm.
oxidation, introduce oxygen in a vacuum chamber as well, but it is not recommended to use oxygen because we have a turbo pump. It doesn't have a efficiency to remove the oxygen from a vacuum chamber where in a rapid speed. That is, we almost use the chamber is useless for 10 to 12 hours if there's a oxygen impurities in the vacuum. We have oxygen impurities in a chamber. That is, it will oxidize our targets as well. Na?
Mhm.
Therefore, it is recommended not to use oxygen inside a vacuum chamber. Or if you use oxygen, then there will be you may left the sputtering chamber in a vacuum for 12 to 14 hours, so that the turbo pump can eliminate the oxygen contents from the vacuum chamber. Na?
So then you use oxygen just to prepare your aluminum oxide, correct?
Yes, yes, Professor.
So in this particular case, how looks like your structure? You have in your oxide grain boundaries or things like that?
Professor, the simple procedure for the oxidation, I use that I introduce oxygen inside a chamber with a specific pressure like 25 millitorr. Then I oxidize, I shine the shine my substrate with the oxygen plasma. We have a facility in a Turant 1. That is, this is a place in a vacuum in our vacuum chamber. We can shine our substrate with the oxygen plasma as well. This oxygen plasma also oxidize the layers we needed. Na?
But which kind of oxide you have? A polycrystalline or you have amorphous oxide?
It doesn't matter because for aluminum oxide, now it can be amorphous. It is amorphous.
Okay, because it means you exclude completely the formation of grain boundaries.
Yes, Professor.
Yeah.
Because we can crystallize aluminum oxide in an annealing process as well. No?
Yeah, but my
If we
main
require.
question is that for a TMR junction, for instance, if you want a good tunneling barrier, you should avoid grain boundaries because there you have oxygen vacancies and you have transport across these junctions. This might affect your junction, dissipating heat and things like that. Yeah, my point is how can you ensure that you don't have such grain boundaries? How can you access this information?
We have what we call FMM, ferromagnetic. What we can study the surface properties with the AFM. We can
But
study the.
did you do that?
No, because I never require because for we can get the TMR with the amorphous aluminum oxide. Na?
So you
Uh,
assume that you have amorphous.
Yeah, further we can do the surface treatment with annealing na, at different temperatures. This also increase the
Actually, not really, depending on the condition. Actually, if you have amorphous humidity heat treatment, you actually create polycrystalline structures. Yeah, that's a bit controversial, but you should. Yeah, my point is, if you have amorphous or polycrystalline, can you distinguish this from your measurements?
We do the XRD of our samples now for checking the crystallization of and amorphous state of our samples.
Okay, so then you measure the
with
XRD.
XRD, yes.
And then it means you can be sure that it's amorphous because you measure the X-ray diffraction.
Yes, Professor.
Okay, so that's what I was expecting to hear from you. Yeah. So a little bit further in your slide 17, yeah, you show your setup measurement, your measurement setup that you have a coil, you have your probes. How do you measure your magnetic field nearby your device?
Magnetic field nearby, we have a voltmeter now. We can measure the which one slide?
17.
17. Slide 17. This one.
I cannot see you. You have to stop sharing a presentation and place your presentation. Yeah.
Okay. Professor, we have a okay. Okay, how to do this one? I don't know.
Stop sharing your text and share your presentation.
Okay. Stop share. This one. Here, Professor, these Helmholtz coils are connected with our KEPCO source, magnetic field source. Na KEPCO, we have a KEPCO which is KEPCO is used to apply a magnetic field in a Helmholtz coils. Yes, and then we can verify this with a voltmeter as well. The strength of the field.
Okay, so it was previously calibrated, yeah. So you
yes,
know.
Professor. Yes.
Okay, that's my question. So you don't really measure while assessing your transport properties, but you have previously gauged your system. Okay.
There is a source here. I have not shown here in this picture.
All right. So a little bit further on the slide 21, if you can move a bit. Slide 21. Yes. So you presented a lot of structures. Yeah, you prepare a lot of structures. It's quite a nice volume of data. Yeah, I think in your thesis you should really be careful how you put this story together. Otherwise, it looks like a patchwork. You know, you did a lot of stuff, but there's something I missed a little bit. Yeah. For instance, how are the novelties of your work? What's something new you are addressing? And this should be the main focus of your work. The rest is I mean, you can use as a supported data, but I think your reader should catch in the introduction what is new, and then everything has to go in this pathway during how you present your data, your review, literature review, and then finally the way you present the data and how you make your conclusion. Looks like you have different projects. That is nice. That's what the PhD is really done. You have to probe different things, but your thesis is some story you have to tell people. And then since it's a PhD, it should be something ideally something new that you found by yourself and you discussed during your PhD. I miss a bit because I saw different views of your work, and I really miss a bit this. I mean, I can grasp here and there what should be new, but I should be something really automatic. Yeah, I should get the first in the abstract, and then in the introduction say, okay, this is the novelty. Let's see if this is really true. Yeah, and go further. And then when I see this structure, you know, I do transport in organic materials. I'm not really the full expert. I know what magnet resistance is. I know the basic structures for spin valve and so on. Yeah, but I'm not really the guy that understands everything. So when I look at the structures, I can see this ruthenium 3 nanometers. Yeah, my first question, why do you need this? I mean, why this is important?
Yeah, this is a basic bottom electrode. Now we need a bottom electrode for a application point of view. And this is a bottom electrode, and this is a top electrode for the electrical properties. We use this one. No? Also, it helps the growth of a nickel iron and a bottom ferromagnetic electrodes.
But why ruthenium? Why you need this? Why not gold or silver or another metal?
Yeah, we can use we can also use titanium. I also use titanium here, like tantalum here. Uh, the basic reason for using this has a better conduction with respect to other metals. I have also produced samples with titanium, tantalum as well.
It means, I mean, the main property
Is
you look
that
for
the
is
conduction
condu
of
conductivity.
conductivity? Yes.
Yeah. Okay. So that's the main focus. Okay.
Yes.
During your written text, you place in some parts in one structure. Remember, you don't have to go back. There buffer layer.
Yes.
Yeah. What is the buffer layer? Why do I need this?
Yes, Professor. In a complex structure like magnetic tunneling junctions, we need a better buffer layers, like better conducting layers, so that we can measure the transport properties as well. And the for the growth of in a magnetic tunneling junctions, we grow the nickel iron at the bottom. We try to grow nickel iron at the bottom, so that for a nickel iron for growth of a nickel iron we all because nickel iron grows as a 111 so we try to use the titanium so because it has a structure like a 111 plane so it
So
will grow more smooth.
okay. So there is also a texturing process. Yeah.
Yes, yes.
All right. So let's go. Let's go to your TMR junction. Can go to the next slide, please. Let's see if it's this.
This
Oh
one.
yes, exactly. Yeah. So you went quite fast here in this explanation.
Yeah.
I didn't have time to look carefully the difference from one to another and how this
Yes.
impact. Yeah.
Okay.
Um, why you have a higher hysteresis on the graph in the right side
Okay.
by changing the nickel iron by
Cobalt
the
iron.
cobalt iron.
Yeah, yeah, Professor. Nickel iron is has a because nickel iron is considered as a soft ferromagnet. Na? It has low coercivity. You can see a soft ferromagnet always has a low coercivity. These has applications. This kind of a system has applications in a switching switching
Mhm.
while the cobalt iron is considered while the cobalt iron is hard ferromagnet a hard ferromagnet always has a higher coercivity you can see here these kind of exchange bias can be used as a memory elements this can because for a reading and writing we need a higher coercivity so that the during the operation it will not change its polarity so it will
Perfect.
not demagnetize so that it is
Okay,
easy to
this I understood very well. I mean, this was quite clear. I could see that the nickel iron was
yeah
responsible for one
yes
property, and the cobalt
yes
iron was responsible for the other
yes
property. And you mentioned that this is well known. Yeah.
yes Professor.
So it means how was the main goal for you to do this investigation?
This
What do you
this
want to learn there?
yeah this is for application point of view. I have used this kind of exchange bias in my spin wells for if they were these structures were considered as to use in a memory elements. This is the main goal. It has a higher coercivity and file for the switching applications we use a nickel iron that it has a low coercivity that we this can be used as a switching application.
Okay, so look, can go to the next slide now that I see.
Here is a bottom pin, na?
Yeah, that's exactly what I mean. And then you
Yeah,
make
this
a
is
set, you sandwich both structures. Yeah.
yeah, Professor. This is very interesting work. Now, this is a new work. You can see here, na?
Yeah, that's
Yeah,
this is exactly where I want
yeah,
to
this is
arrive.
a new work, na?
Yeah, because it's a new work. And then I want to know
Yeah,
exactly the previous slide show that you something fundamental that is done in the
yeah, yeah,
literature, and
yeah,
you want to learn something that
yeah, yeah.
can contribute to exactly this slide. Yeah,
Yes, Professor.
that's the point where.
This is a novel work, na?
Okay, so then, okay, now I see they have a Nikon wire there. If you go to the previous slide, yeah, you see the, I mean, the left side is somehow similar to the next one. There is just missing one nickel iron layer, right?
This is called exchange bias, na?
Yes.
Due to this medium mechanism, na, this loop is shifted from zero, na? This is
All right.
exchange. Yes, this is
And then
exchange
go,
bias, and
yes.
this is another exchange bias, na? With the nickel iron as a seed layer. This you see here. This nickel iron has a configuration. If you measure the, it has a 1-1-1 plane. If we
Mhm.
grow first and then we grow the remedium mechanism, then it has an exchange bias. Without this layer, the remedium mechanism doesn't have a exchange bias with this one. It helps the building of the exchange bias with this.
Yeah, that's the point where I want to come in your work. I think all these devices has to be somehow connected in your story. Yeah. For you come to this point, you'll be able to fully understand what you just prepared, you just characterize. Yeah, you
Yes,
have to understand the previous slide as well.
yes,
That's what to
Professor.
make a story. Yeah,
Yes,
is
Professor.
not there because it's nice and there is application. Is there, of course, there is application by itself, but
Yes,
support your conclusion in the device, in the device structure, in the layer structure that is new. Yeah, that's the
yes,
point.
yes,
Otherwise, I mean, you have to state what is new, what is not new, and why
yes,
you did what you did in something that is not new, because you need to
yes,
understand, yeah,
yes,
step by step in a systematic investigation how things goes. Yeah.
yes.
So the last point is in your fabrication process, you told me that you use shadow masks.
No, Professor, I didn't use a shadow mask. I used a hard
You
copper mask
okay?
that
All right.
has a dimension of a millimeter size.
Sure. Okay. So then that I misunderstand during
Yeah.
during your presentation, because when then you talk about hard mask, I somehow interpret as a shadow mask. Okay, so I think that's all. I mean, congratulations for your work. I mean, I guess most tricky questions Lucy already did on the working. So yeah, I'm done.
Thank you, Professor.
Rubem, is back to you.
Ok. Obrigado pelos comentários, César. É muito engraçada a defesa, porque a gente fica se coçando aqui para não comentar, não contribuir para a discussão, mas esse rito é bem diferente. Então, vamos passar então para o professor João Paulo Sinecker, para você tecer suas considerações e arguir o candidato.
Well, thank you for inviting me. I have been following your work here at CBPF, at the labs. I know how dedicated you are. And of course, the result is there. You have many results, many studies, and I think this is very, very good. Your presentation was very good. It clarified a lot of things that your text only bring us to some doubts. So congratulations. And I think you can, based on your presentation, what you have said, if you pass this in your mind afterwards, and read your text, you will see the mismatch. There is a mismatch between your text and the text is not bad, but there is a mismatch between what you presented and what is written there. And I think Lucio and Cesar have pointed out some very important things, and that you can improve in your thesis. Of course, you don't have to correct this text because this text is just for fulfill the ritual here. But you have to keep in mind that most of the things that have been said to improve your text. Many of the observations concerning the results and so on, I think they were already pointed out by Lucio and Cesar, so I will not repeat myself. But one thing that I think I should say, it was especially Cesar said, that what I missed was really the novelty. I mean, what is your contribution? Yeah. Now it's clear. We have seen your presentation. It's clear after the questioning of Cesar. It's even clearer. But in your thesis, you have to make this a really strong statement. There, you should say what is your contribution for the system. Yeah. This is very important. Yes. Which will be your publication, which will be the result of your work. Yeah. So please do it. Yeah. The text have some. I made a lot of notes, and I will bring the text to you. I will let you in your room when we meet here. I did it by pencil, so and pen. So I printed it, and so it's easier to give to you than to scan and send by email. I would just hang it to you. You shouldn't. I don't mind if you don't return it to me. It's okay. And so there are many questions in the text that I made many appointments that perhaps helps you to improve your thesis. No, okay. One thing which is really I noticed is that somehow you messed up with the references. So the references in the text sometimes doesn't refer to the references in the list. They are out of order somehow. I don't know if I know that working with Word or yeah. not a LaTeX.
Yeah, Professor, I am writing a thesis now in a LaTeX. Now I have.
Then it's easier because then LaTeX does it for you. Yeah. But here I noticed I was curious about some references. Then I went to the reference list and said, "Wow, but this is not the reference that he's mentioning. It's another one." So be careful with that. Okay.
Yeah, Professor. Now I am using LaTeX.
There are many out of order.
Yeah.
Also, the definitions, let's say magnetic tunnel junction, the MTJ. You use it before you define it. Then you define it 2 or 3 times along the text. So pay attention on these things on your thesis. This is just formats. No? Okay. One thing you in chapter 2 where you're making your fundamental background, you say some things about basic concepts. I think I like most the figures you show in the presentation than the figures which are here. So I believe that you will be putting that on your thesis, not the. I mean, there are many figures here in the thesis in which in your presentation are better. Not quality. I mean. For instance, if you go, let's go to the slides, the beginning, where you're showing the first structures. I think there, if you put in the first or second slide, I don't know.
Yes, this one, 2.2.
I'm not seeing here. Just seeing because we're just seeing the change it in the PowerPoint, which is not being presented, please. Because in my screen, I just see the PowerPoint, not the presentation.
Okay. I will show the qualification. Will I show the PowerPoint or a qualification text?
No, the PowerPoint.
Okay, PowerPoint.
So nevertheless, this is what I'm saying is that some figures in your presentation are better.
This one?
No, I'm seeing again. Yeah, okay, you can go up.
Okay.
For instance, slide 6.
Slide 6 here. This one.
This representation, and I mean, this kind of thing, it is not so clear here in the text. So in the thesis, be careful just to make it by. Okay.
Yes.
So in the fundamental record, for instance, you're saying about basic concepts. Then you say some few words about gyromagnetic resistance. Here in the presentation, you cite the Nobel Prize winners, Grunberg and Fert. And but here in the text, you didn't cite them in the magnetic resistance.
No.
And they won a Nobel Prize for that, so it's worth to mention them. And also Mario Babic, which is a Brazilian.
Okay.
And then you speak about tunnel junction, but you say you don't speak a lot of spin valves. And afterwards, you all your devices are spin valves. So okay. It is somehow in the text, but pay attention of that. Perhaps you should introduce that, okay?
Okay.
What else? Yeah, some schematics that might help. That I think it's better. And I made a lot of notes here. I will pass to you. Okay.
Thank you.
So at the end, I think what is the most important thing is that what is your original contribution, as Cesar said, and for instance, at the end you say it is not clear the objective here in this text. It's not clear the objective what you're trying to do. So you said, for instance, at the last sentence, you said the results obtained in this project will allow us to understand the basics of transport and dynamic properties of these magnetic systems. This is already more or less known. I mean, the basic physics of this is what you showed. So you have to improve these texts to show what you have changed in these structures. What is the effect of these changes, and why this is important? Yeah, as Cesar mentioned at the end.
Okay.
So you have to tell the story in a better way, I guess. But it's clear that you made a lot of work. That you learn how to grow this structure, which is not a simple thing to do.
Yes.
Once they are already grown and you measure them, it seems simple, but I know how many hours it takes and experience your day-to-day life here in CBPF. So I know how much you dedicated to this, and your group, in fact, the whole group is dedicated to this. So I congratulate the group and you for the choice of the work, and I believe you'll be able to improve this and make a very good thing.
Yes, brother.
Okay,
yes.
I think I'm done.
Okay, thank you, Professor.
Obrigado, João. Agora, qual é o protocolo agora, Ricardo, João?
Eles vão passar a gente para outra sala.
Para vocês fazerem.
Para a gente fazer a deliberação. Se vocês esperam um pouco aí, talvez demore um pouquinho.
Tá bom, a gente fica ligado aqui.
Bom?
Posso passar?
Pode.
Bom trabalho.
Obrigado.
Acho que foi todo mundo, né?
Só ficamos o Diego, eu e vocês dois.
Tá tudo certo.
Sim.
Conseguimos. Voltamos.
Ok, estão todos aí?
Sim, sim.
Sim.
Eu vou projetar aqui, tá?
Procurei uma musiquinha paquistanesa para botar para o Asmat depois.
Cadê o Asmat? Ele tá aí?
Não entendi nada.
O Asmat tá aí ou ele foi...
Tá aí. Ah, tá aqui ele, mas não.
Asmat?
Vou chamar por...
Yes, Professor.
Ah,
I am here.
You are here? Diego?
Yes, I'm here.
Okay. Can you see the screen?
Yes, Professor.
Okay, so the first words are just documentation. Okay, so we have met. I'm not the president, but anyway, I'm saying, considering the originality of the subjects, we consider it a very good. The relevance of the proposal is good as well. The proficiency of the candidate it's excellent for the proposal. The potential for publication is also considered to be excellent, and the possibility of the conclusion in the 48 months, it's high, but of course we know the problems of the pandemic and so on, the restrictions, so we consider it as high in normal conditions. Yeah. And we made a short report, so o candidato fez uma boa apresentação, mostrando o domínio do tema e respondendo de forma segura as indagações da banca. A banca sugere que as recomendações feitas durante a admissão e nas anotações do texto apresentado sejam usadas para aqui tem um grupo lá, escrita da tese final. E o projeto tem grandes possibilidades de publicação e de finalização no prazo. Então, no final, você foi considerado aprovado, tá? Por todos os examinadores. Parabéns. E, Rubens, se você quiser falar alguma coisa, Diego, se você quiser falar alguma coisa.
Do meu lado, eu agradeço a participação de vocês e as sugestões. Todas vão ser incorporadas na tese, né? Depois eu deixo o Diego falar, depois eu faço um comentário geral sobre o Asmat.
Bom, eu também agradeço a participação de todos, os comentários também foram muito bons, inclusive teve coisas que eu não sabia mesmo. Sobre Asmat, bom, ele tem trabalhado muito especialmente estes últimos meses, tem inclusive sábados, domingos, e acho que ele fez uma boa apresentação, teve algumas coisas que faltaram, focar realmente no que é novo do trabalho. Ele, da parte técnica do sputtering, ele maneja muito bem a engenharia das camadas, que boa parte da tese, bom, da apresentação foi isso. Ter uma boa engenharia para fazer estruturas reproduzíveis e depois conseguir usar essas estruturas para fazer física nova, que o análise de spin pumping, damping, essas coisas, né? E, bom, por enquanto é isso, acho que já na tese a gente vai apresentar bem os resultados que a gente tem. Obrigado a todos de novo.
Só um comentário, é isso mesmo, a parte nova é aquela análise de dumping, alargamento de linha, camada por camada, que a gente tem condições de fazer, mas isso o Asmat começou a mexer nisso há menos tempo, então já estava rodando o prazo, então ele não desenvolveu tanto ainda a ponto de vender bem esse peixe, né? Porque ele gastou realmente um esforço muito grande para aprender a fazer essas amostras e reproduzir, etc. Tanto que agora a gente está fazendo algumas lá para a tese do Leishon, já mandou algumas para lá, porque a ideia é que o Leishon é um aluno meu e do César que vai fazer um dispositivo mesmo com base nisso. Tem a função transferência, tem tudo, e ele vai usar, ele fazer eletrônica, então, para uma tese no mestrado em instrumentação científica. E também, né, essa parte, assim, ela é uma parte importante como um dos componentes, né, de estruturas mais complexas, esses nano-osciladores aí que geram micro-ondas, ou geram funções de dezenas, centenas de megahertz, quando coloca lá em cima daquele pilar um vórtice, né? Ele tem uma série de aspectos assim que o Asmat ajudou a pavimentar, que a gente estava sentindo falta no grupo de manter essa linha ativa. Assim. De resto, eu queria dizer que ele é um cara muito bravo, assim, it's a brave man, porque ele veio do Paquistão em novembro de 3 anos e um pouco atrás. A mulher dele faltava 15 dias para ganhar o nenê. Ele só foi ver o filho, acho que depois de 2 anos, não? How old was your son when you saw him for the first time? Your kid?
Almost 4 years.
No, your kid, because your wife gave birth right after you arrived.
Yeah. Around 3.5. 3 years. Because I didn't go in Pakistan last 3 years.
Maybe he's doing something that we wouldn't be able to do today. I mean, I wouldn't, right? So he's a brave man. He thought that it would be possible to bring his wife, but the cultural differences are so hard to handle at this moment and to get the thesis done, etc.
Yes.
And I think that's it. So it has been an honor to work with Asmat. Sometimes he's a tough guy to convince to do this or that, but he worked very hard. Então é isso, minha gente. Obrigado aí.
Ok. Eu já mandei para a Beth o parecer. Aí o César e o Lúcio pediram para mandar a Beth por o PDF para eles. Tá? Eu mandei nas 2 versões para você. Mas manda o PDF para cada um. Primeiro manda para um, depois manda para outro. Tá bom? Quando receber o assinado, aí manda esse PDF para o outro. Tá bom?
Ok.
Ok. Você
Tudo bem, gente? Posso encerrar a reunião?
Está encerrada a sessão. Obrigado a todos.
Cuidem. Obrigado.
Um sorriso aí que eu vou bater uma foto. Pronto. Aí eu mando uma foto depois pro Rubem e ele distribui.
Beleza.
Se cuidem. Tchau.
Thank you.
Parabéns.